Hi everyone, thanks for coming. Today I'm going to talk about my work on provable guarantees for non-convex and convex optimization in high dimensions. So today we have data deluge. Data is coming to us from various sources, from sound, video, images, social media, and so on. And the problem is that once we get new data, as the amount of data grows, we have more variables we need to estimate. So we are in high dimensional regime. And the problem is that a lot of times this information is lying in a low dimensional structure, which makes learning with big data an ill-posed problem. So it's like trying to find a needle in a haystack. And in order to find that needle, we need a lot of computation, and it's computational and statistically challenging. So so we want to learn in big data, and the goal is that we are modeling it in terms of optimization. But why are we learning in terms of optimization? Is that most of learning problems can be cast down as optimization problem. For example, in unsupervised learning, if we are looking at clustering, whether k-means or hierarchical clustering, maximum likelihood estimators, probabilistic latent variable models, and in supervised learning, if one famous example is trying to train a neural network. So in training a neural network, we are optimizing with respect to a loss function. And optimization has two classes of areas. One of them is convex optimization, when we have a very nice looking loss function and we have one global optima, and it's not that difficult to get to the global optima. In non-convex optimization, we have multiple local optimas, and as dimension grows, possibly we have exponential number of local optimas, which makes it a very difficult problem. But the thing is that a lot of times interesting problems that we have in machine learning are a non-convex optimization problem. So the question we ask is that how to deal with non-convexity? So there are two approaches. The classical approach is to do a convex relaxation of the non-convex problem, and then once we find the global optima for the convex relaxation, try to model how close it is to the actual optima. The other approach, which is a more recent approach, is to directly look at the non-convex problem and try to come up with some instances of it that are doable, meaning that this local optima is actually part of the solution, or with some mild assumption, we can actually get to the global optima. So I have worked on both classes of problems, and today I'm going to talk about two classes of my works. The first one is looking directly at non-convex problems, and we have provided a method for training neural network that has guarantees to work, and we use tensor methods. So essentially, tensor and matrix algebra are some class of non-convex problems that for them, there is some hope to actually get to the global optima with some mild assumption. And for the second part of the talk, I'll talk about my work on convex optimization, where we looked at problem of convex optimization in high dimensions, when we know that we have curse of dimensionality, and earlier approaches to convex optimization, they don't really work well in high dimensions. So getting into the first part of the talk, so today, I don't know why this jumps so much, sorry. So today we have a lot of cases of successful applications of neural networks, and everyone uses backprop. And we know that training neural network is a highly non-convex problem, and there are documented cases that backprop can get stuck. So in order to give you a more intuition of how backprop can get stuck, I'll start with a very simple example. So we have a toy example. We have some labeled samples. This is the 2-dimension of the input, and then we have two classes. So red ones are class +1, and then green ones are class -1. And I have a 2-node neural network, which is enough to classify this, because essentially we need to figure out these two lines. So if we look at the loss surface for this problem, in order to be able to sketch the loss surface, we randomly draw one of the weights fix them and then sketch the loss surface in terms of other weight. As you can see, the loss surface has a surface of local optima, which is actually a bad local optima. So what we do is that we reformalize the problem of training the neural network, and the way we model it is actually in terms of tensor methods. And what happens is that our method gives you a locally convex loss surface. So as long as you can guarantee to start it somewhere around here, you actually have guarantees to converge to the global optima. So, but let us get into an intuition of how we do this. So there's always been the debate in generative versus discriminative models. In generative models, we look at the joint distribution of input and output. So for example, in this case, if we have a binary classification, we have the joint PDF looks like this for class 1, and then it looks like this for class 0. In discriminative learning, we look into conditional probabilities, and that's how it looks like for these two classes. So the thing is that neural networks are discriminative models, and they are in general, and training a neural network is in general an NP-hard problem. So the question we ask is that if we have some information of the input distribution, if we have some assumption on generative model, how does this help us in this discriminative task? So what we do is that we learn some feature transformation of the input to train the neural network. And the idea behind it is that we have a lot of unlabeled samples, so we can use them to learn some features of the input, but some sort of features that actually help us. And I'll tell you in a bit what sort of features we form. So the other important building block of our work is that label has some information about the input. So if we form the cross moment between input and label, there is some hope that if we form a good cross moment, it might have some information about the discriminative features. So then the question is, what sort of moments we form such that it actually helps us? We claim that this input feature that we learn, if we form the cross moment between this input feature and the label, this is actually having hope to give us information. But before we get into that, let us make sure that we are all on the same page with this notation. So this notation is outer product. So in a simple case, if we have two vectors, the outer product of two vectors, x and y, is nothing but x, y transpose. So if you look at I1, I2 entry of this outer product matrix, this is xi1 times yi2. So if we have more than that, we are just essentially having higher order matrices, which we call them tensors. So now if it's three of them, it's a three-dimensional matrix or a three-dimensional tensor, and then essentially it has the same idea. So any questions so far? So let us get back to the feature that we learned from the input. So the features we learn are called the score function transformations. And in the simplest case, the score function is an idea from statistics that if we have some vector input x that has some PDF p of x, the score function is nothing but derivative of log of the PDF. So if I have a vector input, my score function is a vector again. So what we did was that we generalized this to higher order score functions. And by higher order score function, we mean that the mth order score function is the normalized mth order derivative of the PDF. So again, with my vector input, if I look at the second order score function, it's a matrix. And if I look at the third order tensor score function, it would be a tensor, and so on. So why did we introduce score functions? Why are they helpful? So essentially, the feature transformation we learned from the input is the score function. And if we form the cross moment between label and mth order score function of the input, the good thing about it is that we have proved that if if we have the label function f of x, meaning that if the label is generated by some function f of x, this cross moment gives us the mth order derivative of the function. So essentially, the cross moment between label and mth order score function gives us the mth order derivative of the label function. But why is this useful? Why do we do that? Let us get back to the problem of training neural networks so that I can explain more how this happens. Why is this useful? So imagine we have a shallow neural network. We have input has dimension d. We have k neurons. The first layer is nonlinear, and then the second layer is just a linear combination. So we are assuming that the data is generated from this neural network, which we call it realizable setting. So in this case, our f function looks something like this. Now, if I have some labeled samples, what happens if I form this moment function? So if I form the moment between label and first order score function, it's just using chain rule. So what happens is that it gives us some weighted sums of the weights of the first layer. And these, the columns of the weight of the first layer, meaning and each column is related to one of the neurons. So it's something, I don't know why this jumps on. So it essentially gives us the sum of the columns of A1. So it's collapsing together. It's really not giving us any information. So if I look at the second order score function, it gives us a matrix whose rank 1 components are columns of A1. So if I was able to decompose this matrix, I could find columns of A1. And if we go to higher order, so if we look at the third order score function, essentially it gives us a tensor whose rank 1 components are columns of A1. So the question we ask here is that why do I use tensors? Why don't I use just matrices? The thing about matrices is that in order to have a successful matrix decomposition, I need the columns of A1 to be always perpendicular to each other, which is a restricting case. As opposed to the case of tensors, where with some mild assumption on non-degeneracy, I can actually recover these columns. So in order to have a more general solution, we look at the tensors. And once we recover columns of A1, we can actually use a Fourier technique to recover the rest of the variables, meaning that the weight matrix for the second layer and the biases. Any questions so far? Yes?
That's the can decomposition?
Yes, that's true.
Did you look at other decomposition?
No, we looked at the can decomposition for the most part, because for CP decomposition, we have actually results on how exactly tensor decomposition gives us unique results. And so that's why we looked into that. But there are ways to look into the others. Yes?
This will be just only for one layer of the neural network, or you have like more than one layer neural network, then can you decompose like more than 3?
So essentially, in order to be able to find the weights, just the third order tensor suffices, because we actually have guarantees to recover this. If we go to higher order tensors, it's still possible to recover them, but it just gets more computationally challenging. So that's why we stop here, because this is already giving us the information. And so these results that we have provided complete results for case of shallow networks, and we are looking into case of deeper networks as well, but the idea is pretty much the same. I can give you more details towards the end when I've completely covered the algorithm.
So I guess what I haven't been able to follow is the following thing. You're presenting an approach that has some real advantages relative to backprop, but I don't understand what's been lost.
So what's been lost is that, I'll get into that towards the end, but yeah, essentially the computation is, so if we parallelize them, backprop and our method have the same computational complexity, but we need more parallel processors. So that's the low side of it. So in a nutshell, this is how our algorithm looks like. Let's say we have an input and we have a method to learn this third order score function tensor. So once we have labeled data, we form this cross moment, which essentially is multiplying yi for each sample by this whole score function tensor. And once we have this, we do CP decomposition on it to learn the columns of the weight matrix for the first layer. And then using a Fourier technique, keeps jumping, we learn the rest of the variables. So let us get into the details of how we guarantee that we can actually recover them. So so we have this tensor, and if we have these assumptions that A1 has full column rank, there is guaranteed tensor decomposition, which is work of my colleagues. It's the earlier work. And then in this specific algorithm, we also have the analysis of Fourier technique. So putting these all together, we have proved that if we have samples n, which is polynomial in dimension of the input and the number of neurons, the estimated neural network we form, the distance from the actual function is bounded by order of 1 over n. And this holds with high probability. So this is not in expectation. This holds with high probability. Yes?
So to turn Oren's question around, so what we lose, as you said, is more computation, at least if we don't parallelize it. And what we gain is
we have guarantees that we can actually recover the weights with this precision, and also so we don't get a stock as opposed to backprop, and also we guarantee that the solution we get is actually the global optima. In a lot of cases in neural networks, when they run backprop, they say, okay, this is a local optima, I know, but there's no way I can get to global optima, so I'm just happy with this. But
do you have any, did you try any real-world examples where that happened and this gave a better solution?
So actually, this is a very recent result. We haven't got to that, but the toy example I showed in the beginning is some case of the failure that backprop definitely fails, but this one does. So so far I talked about the assumption that the label was generated from a neural network. What if the label is generated by some function that we don't know? So essentially, the question we ask is that how do we generalize this method to unseen data? So if the label is generated from some other function rather than the neural network, we have two errors. So the approximation error is the error with fitting that unknown function to a neural network, and then estimation error is the error we encounter in estimating the weights of a neural network. So I talked about the first part, the second part, and now let us zoom in more on the approximation error. So the idea we use here is that we know that continuous function with some compact domain, you can arbitrarily well approximate them with a shallow network. And this is the result of Baron in '93. So what he says is that he says, let's assume that there is a label function f of x that's generating the labels. And he looks at the Fourier spectrum of f of x. So if we take the Fourier transform and we form the absolute first moment of that, let's say it's some constant, we call it c sub f. So what he proves is that the approximation error is bounded by this constant over root number of the neurons. I don't want to get into the details of his proof, but essentially his idea is that once we take this Fourier transform, if we take random draws from this Fourier transform, these are essentially related to the weights of the neural network. And that's how we can actually bound this approximation error. So if you want to make the picture complete, this is our main result. So let's say we're approximating an arbitrary function that has this constant c sub f. We have n samples, the input dimension is d, and we have k neurons. Assuming that this c sub f is small, we actually have this generalization bound on the error. So the first part is coming from approximation error, and the second part comes from the estimation error that I covered. And we'll have polynomial sample complexity in terms of dimensions. And as I said earlier, the computational complexity is the same as the stochastic gradient descent if we have enough parallel processors. Any questions so far? Yes?
So I guess the complexity of the decomposition is a function mainly of k?
So the complexity of decomposition is a function of k and is a function of dimension as well. The thing that I need to cover here is that, so essentially it also depends on how we get the score function tensor. Because if the score function tensor is in a form that we call it a factor form, meaning that it has some mathematical form of outer product of vectors, what we can do is that we can do tensor decomposition in a stochastic manner. We don't need to form the complete tensor. We can just use multilinear transformation of the tensor to actually get the results. So in that case, we get very good results. But in general, if it's a huge tensor, the computational complexity is worse. So for example, if we use RBMs to estimate the score function, it gives us a very nice result. Or if the input distribution has a simple form, like let's say it's Gaussian or it's mixture of Gaussian.
I still don't get the intuition behind this score function. That, I mean, the main non-linearity or the main non-convexity comes from this activation in the neural network. And then I don't see how this score function carries with that.
So essentially, the thing about the score function is that we are, so when you're training a neural network with backprop, you are minimizing the square loss, right? And that's a non-convex problem. So using the score, sorry?
The square loss is not non-convex.
In terms of the weights, it's a non-convex problem. So because we have the weights inside these all non-linearities. Exactly. So the good thing about the score function is that using the score function, we are reformulating the problem in terms of a tensor decomposition. Tensor decomposition is also a non-convex problem in general. But the thing about it is that with some mild assumptions, in this case, having the degeneracy assumption on the A1, that has guarantees, whereas for the loss function for the backprop, you don't have guarantees. So that's why this helps us, because tensor decomposition and matrix algebra have this good property that with some assumptions you can actually get the global optima, although it's a non-convex problem.
How often are these guarantees satisfied in like typical applications?
So very good question. Specifically in this case, so as I said, Barron shows that these weights correspond to random draws of a Fourier distribution. So these random draws are with high probability, essentially leads to a full column rank matrix. So with high probability, the assumption holds, so we get good results. And in practice, some of my colleagues have done some works on tensor decomposition, and a lot of times it works well. The thing is that it needs some initialization. So you need to some initialization to make sure that you are close by into that locally convex region. You are essentially in the region of attraction of, basin of attraction of that locally convex part. So in practice, it, of course, like every other algorithm, it needs tuning, but a lot of times it works really well.
That sounds a little bit odd. You were, at the start of your talk, you were casting this as a kind of a global solution, and now you're saying it has to be initialized approximately in the area of the solution.
So essentially what I showed is that it has a locally convex loss function. So it's a locally convex loss function. If you start in that locally convex loss function, locally convex part of the loss surface, you have guarantees to converge to the global optima. But in general, it's a highly non-convex problem too. So in case you start in that region, which is satisfied by in some small number of initialization, and assuming that this C sub f is small, we have that guarantees. But if this C sub f is very big, essentially if you are very far from the actual function we are approximating, we can't give guarantees.
So do you do a bunch of random restarts?
Yes.
How many restarts do you usually do?
So usually like order of like 5-6 times it works in general.
Quick follow-up question. So if that's true, you have to start in the vicinity of locally convex area, and that locally convex is globally minimum. That's what you right. So how does it work if the backprop starts exactly similar position? It's really close to global minimum. Wouldn't it also do reasonable thing if
So yeah, the thing is that the loss surface for backprop doesn't look like that. So it doesn't look locally convex. It looks like this. So if the loss function, if the loss surface for backprop was like that, yeah, but the loss surface for backprop doesn't look like that.
It would converge to something, but it wouldn't be global.
Yeah, or it would even be a bad local optima. It wouldn't be essentially a good
By
one.
comparison, in the same problem in some simulation, that backprop reaches to a solution X, whereas your method goes to better.
So the example I showed in the beginning, the surface that you saw for backprop, there is the one part of surface is completely a bad. Do we have a board here? Okay.
There's markers there. Yeah.
Oh, thank you. So we had this problem, right? There was green here, and then these were red ones. So this is the line that our algorithm recovers. Whereas for backprop, you saw the surface looks something like this. So one of the locally optimal global surface that backprop finds is this, which is a totally wrong one. And this is a and this is a documented case of failure. It's a paper from 1990s. Did I answer your question? Great. So, yes.
Unfortunately, I missed the beginning of your talk.
Sure.
So to me, it looks like you have this binary class classification software. Do you or not?
No. So in this specific case, what I assume that y has one dimension. So it's a scalar. It can be different classes. But essentially, if it's a multi-class classification, it still works. The reason we looked into binary y is that it's a harder problem because you have less information. So that one directly follows. Any other questions? Okay. So I need to mention that this training of the neural network is part of a general framework we have designed, which we call it FEAST. So FEAST stands for feature extraction using a sort function tensor. Our goal is to extract the discriminative features in an automatic case. So the three fundamental blocks we have is the probabilistic model and score function, method of moments, and finally matrix or tensor factorization. And the algorithm pretty much looks the same as the one that I showed you. And I've also showed that in case of mixture of generalized linear model, we can recover the weight vectors. And this is actually the first method that can recover the weight vectors. Earlier algorithms could only find their subspace. And also I've shown that for mixture of linear regression, the algorithm works well. And we are also looking into conditional random fields and recurrent neural networks. So as I said earlier, this is a very recent result, and we don't have complete experiment analysis. But I will shortly talk about a very preliminary results that we are just generating. So we looked into Microsoft Paraphrase data set, which is a collection of paired sentences. And for each two paired sentences, we have a binary classification problem, whether or not they are paraphrase of each other. And of course, it's a hard classification problem because it requires the understanding of whole sentence. So in order to get the score function, we assume that we have convolutional sparse coding model. And this is the preliminary results we got. So this is in the ballpark of the results that on Microsoft Paraphrase dataset. Of course, it needs more tuning of filter sizes and different things. And currently, we are not using any additional knowledge on language structure, and we expect that that would definitely help in bringing up the accuracy and precision. But as I said, this is very recent result. And another thing I need to emphasize is that in experiments, it's really important what we use for score function estimation. So as we improve the score function estimation part of it, it actually generates better results. So the test in general?
For this classification problem, was it baseline, is it 50% or is it skewed?
The chance?
It's close to 50, but this is sort of a mid-range result compared to other algorithms.
That's true, yes. But as I said, we are not done with the tuning and everything. I just thought I'd let you know about it because This is very recent. And actually, in the beginning, we started for forming the score function, we used denoising autoencoders. And we realized that they are not very good options for training the score function. We are replacing them with RBMs, and we expect that we get much better results. So it needs additional work, definitely.
Can you explain how you would use language structure to improve your method?
So essentially, it should come in. So what we do is that we form this score function tensor, this score function feature transformations. So I think the way that comes in is that it adds some additional features to because finally what we do is that we find some discriminative features as an output of the tensor decomposition. Then we project all the features in that direction, and then we do classification. So what I'm expecting is that it actually adds additional features before the classification part. So it would definitely help with the classification in the end.
And does that interact at all with your guarantees? Or I mean, if you add more features, doesn't that change the surface?
So essentially, here we are not talking about training a neural network. Here we are just saying, okay, I have this whatever data set I have. So in general, what FEAST looks like is this. I have some input features. I form the score function. Then I form the cross moment between labels and do tensor decomposition. Once I'm done with tensor decomposition, I have some directions. So then I project my first input features into this subspace, and then I do a classification. So this is I should have explained that earlier, sorry. But yeah, so essentially that's how in general FEAST works on real data sets. So the neural network part and mixture of GLM are some subset of the FEAST framework that we have proved guarantees. But if you want to just run the algorithm on some data sets, that's how we do that.
So I guess I still am unclear. So I think I understood your answer, but I'm still unclear on the notion. If you come to a problem like this, which is a concrete problem, and you say, gosh, I want to have paraphrases, then I can intuitively say, well, gosh, I might think about syntax, or I might think about synonyms, or what I don't understand is what part of what are the variables or the intuitions that your piece is capturing, right? So if I were to augment it, should I be augmenting it with syntax? Should I be augmenting it with hypernyms? I don't understand the relationship between your method and the particular problem.
Right, so essentially here we are using the convolutional sparse coding. So what we are trying to capture is the shift in variance in the sentence. So that's the part that it adds to it in general.
I don't know what the shifting variance in the sentence is.
So essentially it means that the sum, if it's every word has some relation with the words that are in proximity of that. And we are trying to capture that part as well. Any questions? So for the rest of the talk, I want to switch gears and talk about the convex optimization part. So essentially, convex optimization has a lot of nice properties, but when we go to high dimensions, we suffer from curse of dimensionality, meaning that the error is, for a lot of cases, is proportional to dimension or a square of dimensions, so the convergence rate becomes really problematic. So the motivation we had is that a lot of times when we have a lot of data, we want to do streaming and we don't have a storage. So the goal is to do a stochastic optimization. Per new sample, we want to get some estimation. And our goal was to provide some tight convergence guarantees in theory and also have good results in practice. So what we designed. So essentially what we designed is that we designed a general stochastic optimization method that is efficient in terms of dimension. It's based on ADMM. I'll capture a little bit what ADMM is in a little bit. And we get minimax optimal convergence rate specifically for sparse optimization and matrix decomposition framework. And the algorithm has the potential of running on different frameworks, but these two specifically we looked into. And for matrix decomposition, we provided the first online guarantees. So why did we look into sparse optimization? The reason is that a lot of problems in classification, regression, whenever you have low-dimensional structures, such as group sparse vectors and low-rank matrices, in compressed sensing, in a sparse graphical model selection, all of these you can actually model them in terms of a sparse optimization problem. So for this specific problem, so our algorithm is called reason. So as you can see, we get the minimax optimal convergence rate. Here, S denotes the number of non-zeros, D is the dimension, and T is the number of iterations. As you can see, the earlier methods have this square dependency in terms of dimension, where we have logarithmic dependency in terms of dimension. So it's very efficient dimension scaling. And we consider sampling error, so our bounds holds with high probability. And it's not in expectation. Yes.
What is sparsity level?
So S is the sparsity level, meaning that if you're looking for a sparse vector, the number of non-zeros in that vector is S, and the rest are 0. So we also looked into matrix decomposition problem. So this is also called robust PCA. So we have a loss function, which is a function of a matrix, and it's a noisy matrix, but it has some underlying sparse part and low rank part. So as one example, we have, so in case of images, we have an image that has some sparse corruptions, and the goal is to recover the image itself, or in terms of videos, we want to decompose foreground and background, like in surveillance applications. And of course, a very good application of is this latent graphical model selection problem. So in this case as well, we get the minimax optimal convergence rate. So the minimax bound is a batch bound, and this is our framework. And the earlier approaches, they actually get, so we get, if P is the dimension of the matrix, we get P log P dimension dependency, whereas the earlier one have P to the 4 dimension dependency. And we provide bounds on individual errors, because finally the important thing is to how greatly we recover the individual sparse part and low rank part, and again the bound holds with high probability.
Sorry, sure. And so both of these methods, the P to the 4 and your P log P, they'll get to the same global optimum?
Yes, essentially this is the convex optimization problem.
So this basically means you can go up to much higher dimensional models. And
Exactly. Exactly. So in practice, what happened is that, so I'll also cover the experiment result, but in practice what happened is that as we increase the dimension, our algorithm has way better error rates, and at some point the earlier methods just get stuck, they can't give you anything, whereas this algorithm can actually go to higher dimensions and still provide good results. So any other questions? So let us get into the details of the problem statement and the algorithm. So a stochastic optimization, essentially the goal is to minimize the expected loss, and f is our loss function here. And we don't have access to the loss function, we just have empirical samples. And whenever we are in high dimension, as I covered in the first part of the talk, so a lot of times the underlying truth is in a lower dimensional structure, which makes the problem intractable. So in order to make the problem tractable, we need to impose additional assumptions, like the vector that we are looking for is a sparse, or the matrix that we are looking for is a low-rank matrix. And this is done by adding a regularization term, which imposes these properties. For example, sparsity is imposed with L1 regularization, low rank is imposed with nuclear norm projection, and so on. So when we form this minimization, and this is a stochastic optimization, so we need an update for every sample we get. If you look at this as a whole, a lot of times this regularization function have some non-smoothness that makes this an expensive problem to do. So what algorithm we use is ADMM. So what ADMM suggests is that we decompose this minimization into two parts. We minimize with respect to loss function, we minimize with respect to regularization term, and then link them back together using a dual variable. And because of that, it's good for large scale learning. It makes it really cheap. So the algorithm we use is called reason, which stands for regularized epoch-based ADMM for stochastic optimization in high dimension. So what we did is that we have three main components. One is that ADMM works for just one regularization term. We have expanded it to have more regularization terms, so we have made it multiple step as opposed to 2 steps. And we are adding some intelligently designed projections that help with the dimension dependency. And it's an epoch-based algorithm, meaning that once we get the samples, we group them into epochs, and we change our algorithm parameters per epoch. And in terms of projections, so what we do is that for the updates for the main variable only, we do some projections. And the nature of these projections are in terms of the regularization we have. So if you're looking for a sparse solution, we do projection into L1 norm ball. And in the beginning, we don't know where the optimal solution is, so we can start in a big enough ball that we are sure that the optimal solution is in there. And we design our algorithm such that the error is proportional to this radius. And by the end of each epoch, we are sure that the error is halved. So for the next epoch, we change our parameters, but we also shrink the ball. We have designed the algorithm such that we are sure that the optimal solution remains feasible. And since we don't know what's the optimal solution, the best bet we have for the center of the projection is the average of last epoch estimates. So we keep reducing the ball, and that's how we get the logarithmic dependency to dimension, with dimension. Any questions about this? So looking into experiment results, here are the comparison with the stochastic ADMM. And so we look into a linear regression problem, and we look into 2 different dimensions. So the first column is dimension 20. We see that both algorithms are pretty much the same. But when we go to higher dimension, which is dimension 20,000, a stochastic ADMM gets pretty much lost, whereas our algorithm smoothly can converge to the global optimum.
What was the problem? You said linear regression. Can you tell us a little bit more about that?
Sure. So essentially, we have a least square L2 regularization, and so this is we generated the data ourselves, so it's not a real data set. It's synthetic. So essentially, y is inner product of x with theta plus some bias, and the goal is to recover that theta, given y and x. And x is a uniform variable with some additional error. The other comparison we did was with state of the art. So the state of the art is called radar. It's an algorithm from Berkeley, Alec Agarwal and Martin Wainwright. So their algorithm is based on a stochastic gradient descent. That's also designed for stochastic optimization in high dimension. So we look into 3 different dimensions, and we are giving all the algorithms the same amount of time. And as you can see, our algorithm gets much better error results. And one thing I need to emphasize is that a radar is only designed for stochastic optimization for case of a sparse optimization, and it also needs the loss function to be locally Lipschitz, meaning that it cannot be applied to graphical model selection problem, but our algorithm can actually take care of that as well. And in case of computational complexity, the updates we have, all of them are in closed form except for the main variable, which needs projection into L1 ball. But although it seems more complex, since it gets to the global optimal faster, in general, if we give it the same amount of time, it still gives us better results. So it needs less number of updates to get there. We also did some experiments on noisy matrix decomposition problems. So we have a loss function in terms of matrix M, and matrix M has some sparse part and low rank part. And we compared against inexact ALM. The dimension of the matrix is 2000 by 2000. And as you can see, we recovered the sparse part and low rank part with much better error. And again, this framework can also be applied to latent graphical model selection problem. In terms of complexity, theoretically, we need L1 projections and nuclear norm projections. So nuclear norm projections require SVD before L1 projection. What happened in practice was that just one of these projections was enough to get into the solution. So we can, in practice, skip over the nuclear norm projection. Yes.
So what is it that guarantees that when you do the projection, you'll still retain the optimal solution? So that's the approximation you're making.
Right.
Intuition.
You mean practice or in general for the algorithm?
So in practice, you drop this nuclear norm and still you found that it would have.
Exactly. So the thing is that, so in ADMM what happens is that it has a dual variable that keeps track of history of the difference between two variables. What I conjecture is that the dual, and in optimization part we have some, in the loss function we have some penalties that the dual variable is imposing. So the dual variable is, in addition to this projection, the dual variable is also pulling us towards the solution. So when I do L1 projections in the first part, the dual variables is helping me out because essentially the sum of them is the same matrix. So that's what we conjecture. But in theory, we need both of them to provide the guarantees. So in summary, I talked about non-convex optimization and convex optimization. For non-convex optimization, we provided the first guaranteed response for training neural networks. And with efficient sample and computational complexity, this is part of a general framework for extracting discriminative features. And the heart of it is that we use higher order score functions as new features. And in the convex optimization problem, we took care of cursive dimensionality with an algorithm that is fast and is cheap to implement, and we can perform it in parallel. And it gets the minimax optimal convergence rate and outperforms the state of the art. And here are the list of the papers that I covered in the talk today. Any other questions? Thank you so much for your time.